and welcome to Determinedly Deterministic. My name is Raf. We are here joined by Nick. If you have any questions, put them on Slido. Who are we? Well, we are developers. I'm an open source contributor. Been Java dev for a while. Similar to Nick. Apart from coding, we're also hobbyists. I'm jumping out of fully functional airplanes from time to time. Nick is a sailor. But let's not talk about us. Let's talk about LMAX first. What do we work for? So LMAX is a financial exchange. LMAX is a leading independent operator of multiple institutional execution venues for FX and cryptocurrency trading. Our main clientele are the big boys, funds, banks, brokerages, professional traders, people with big pockets interested in grabbing a piece of the market, try their luck. What they do expect from the product that we provide is a strict price and time priority order execution. Our main entity that we maintain as an exchange is an order book. Order books are basically collections of orders that our clients place on our platform. They are ordered by price. If there are two orders that have the same price, they are ordered by time. It is imperative that whoever gets to put an order first will get matched against the opposite order, and it will not be the guy that placed the order after him. Given the nature of our line of work and the product that we provide, we have a very high performance expectations. Our clients are mainly institutional. They have lots of money to spend on their high-frequency trading algorithms. They are placing hundreds of thousands of orders per second. And what they expect from us is a very high, very tight latency. These numbers, you can find these numbers on our main page. These are the official ones. The actual numbers, the 100,000 per second sustained, is just a boring business as usual second. 800,000 per second peak. I believe we can do more. What does it cost inside our system is sometimes the inter-service traffic can reach millions of messages per second. How do we deal with that? Disclaimer. All the opinions expressed are our own, not LMAX. Why are we here? Nick?
Yep. So we're here because we think deterministic systems are good, hence the talk. We think concurrency is hard. I think most Java developers would agree, or any developers. If you have more than one thread, you're inviting a lot of problems, especially when it comes to deterministic processing. And we also care about performance, especially in our line of work, but especially Raf. In his hobbies, his open source contributions, performance is a big part of it. And performance can be gained or lost by doing a deterministic system. So deterministic system, said it a few times, it's in the title of the talk. But a few of you might not know what a deterministic system is, or potentially what the word determinism means in this context. So, Raf.
Right, so what is determinism, right? I did a quick Google search, and I got a result from Britannica saying that determinism entails, in a situation in which a person makes a certain decision or performs a certain action, it is impossible that he or she could make any other decision or performs any other action. However, that doesn't apply to computers. So if you replace it with system, that makes a bit more sense. But still, what is determinism is the wrong question. Fortunately, some smart brains figured out that providing a definition of a deterministic system is a good idea. So a deterministic system is a system in which a given initial state or condition will always produce the same result. There is no randomness involved. Every time your input gets processed, for the same input processed billions of times, you're going to always produce exactly the same result. What are the benefits of a deterministic system? Why would you want to have a deterministic system, deterministic service as a part of your architecture? One of the reasons is the simplicity. What we're going to present in the next few slides is a pattern that will show you how to implement, how to turn part of your system to be deterministic. What you're going to find out at the end of this journey is that the architecture is actually very simple. You're going to get ultimate debuggability. What do I mean by that? Have you ever replayed any production traffic on your local machine, then collected the results from your local computer and uploaded it back to production? There are use cases for that. Have you ever debugged a production issue that is impossible to reproduce locally, simply because the way your production systems are set up is vastly different than your laptop, and you basically cannot reproduce all the variables. In a deterministic system, it is very easy. It is very easy to fail over when one of your services go down. We're going to explain you how to do that. And ultimately, you can achieve extreme speed. What do I mean by extreme? We're going to tell you in a moment.
Yeah.
Nick.
So, an example system that isn't deterministic. We work both at a financial exchange. So you might imagine orders come from the internet to some kind of gateway, which can parse those orders, JSON or potentially FIX, which is a financial protocol. And it's going to parse those to forward them on to an internal system. And Raf mentioned that kind of order book and that kind of core part of the exchange, which is typically called a matching engine. So the gateway is going to forward those events onto the matching engine. If a customer is wanting to trade, we need to see, are they allowed into the system? How much money have they got? Can they do this trade? So we probably end up with a user service as well. Hey, microservices are great. And all these services are going to talk to each other. The gateway is going to talk to the user service. Is this person allowed in? The matching engine is going to talk to the user service and find out whether they've got enough money to do the trades that they're requesting to do. This is great, but we've kind of smeared our state across several services. The user service owns information, say, about account balances. People might be updating those also via the internet. People might be adding money to their account or withdrawing it. If they're doing that, that will happen asynchronously to the trades occurring on the matching engine. So what Raf was talking about earlier of replaying, events that happened and getting the same result. It's probably not really going to work here because you've got state everywhere and you can't replay it all in the same order. Concurrency is hard. I think we'll come back to that. So a system like this, we can kind of spot a few key identifiers where determinism might help you. So frequent updates of shared state. Have you got state in many places? Are you updating it often? Deterministic system might help you there. Concurrent updates to shared state, that might be okay. If eventual consistency is all right by you, great. If you've got clients that really want strict price and time ordering, however, maybe less good. So concurrent updates to shared state might be a problem, and if you see that, a deterministic system will help you. And yeah, if ordering is important, a deterministic system will really help you. The question is, how do we put it into practice? Raf?
Right. So, TLDR, if you really have to run, there are three main points that most deterministic systems should provide. A few features. You should record all of your incoming traffic, or rather all of the inputs to a deterministic part of your system. You should only update states using one writer. There should be no instance at any point in time where multiple writers try to update and change a state. And also, you cannot produce anything, any side effects that you cannot reproduce later locally or at your replicas or any other service. Simple example. Imagine that you have some inputs into your application and some outputs. And this application wants to update some states. How would you provide an input to a deterministic, to an app in a way that it will become eventually deterministic? You could use a buffer or a queue. The application can take an event from the queue, update its states, produce an output. However, do you really want to use regular buffers or queues? We work for LMAX. We have disruptor.
I don't think we can let it slide with a regular buffer. We need a circular buffer, which is what the disruptor is. So for people who don't know about the disruptor, LMAX created it, Martin Thompson and friends, back in about 2011. It's a ring buffer, which is a regular buffer, and when you get to the end, you start writing at the beginning again. It's got a few extra bells and whistles. It's not just a ring buffer, this library. But if you've got inter-thread communication, having that buffer between them, very useful, and the disruptor gives you a lot of nice tools to help you with that. There is version 4, by the way, which is coming soon. Not quite yet. There is a release candidate. It hadn't been updated for a while, so it's now got Java 11 support, and a lot of the old Sun MISC unsafe is going. But anyway, that's a disruptor. Let's get back to where we were.
Get back to ring buffers. So the main point of using a ring buffer is that everything that goes into the ring buffer goes in a very specific order. Everything you take off the ring buffer, you take off in a very specific order. Also, every slot in the ring buffer has its sequence. Every method, every event you put in and put out has a particular sequence. It's very easy to access all the elements of the ring buffer in case you would like to replay or retry a part of a ring buffer, or even the whole ring buffer if you want. It's very easy to do that. So when you have an application, in this case, let's make it a thread that takes off the first available element on the ring buffer, the head or the tail. On the other side of ring buffer, you're still accepting outputs and publishing your payloads to the next available slot. Once your application thread updates the state, execute your business logic, you put it back on a different ring buffer, which has which has exactly the same mechanics.
So yeah,
Let's talk about journaling.
Yeah,
We are talking about replaying states, replaying your traffic.
yeah. Well, I think more importantly is that one of the first bullet points we had earlier was about recording everything going into your system.
Yes.
And journaling is that. So if we've got this buffer, we can process those events, but first we could record those events, and that will give us that replay. That gives you that excellent debuggability, because you can bring those journals to any other machine and run them through. And if your system is deterministic, it will give you exactly the same outputs as any other run through. So this we call journaling. Quite a few frameworks have it. And yeah, if it didn't journal, it didn't happen. If it's journaled, it can be processed. If it hasn't been written to disk, we won't process it. Because if we processed it before we wrote it to disk, it kind of ruins some of that deterministic flow. And when we've got these journals, we can replay them through the same system, get the same outputs. So pictorially, we have our data going into an empty slot of that ring buffer. And we have the oldest bit of data being read, and it's being written to disk, a journal file. Then our application process can read that same event and process it, generate its outputs. So that's journaling, one of the steps on the way to a deterministic system. Once you've got this kind of sequenced order of reading these events from the ring buffer, we can do a bit more. So replication. We can have more than one instance of the same service. If we treat one of them as our source of truth, then we can replicate it to the other one. And if our system is deterministic, it's effectively a replicated state machine. This will give you some level of fault tolerance. It does mean that you have to fail over, and while you're failing over, that 80 microseconds latency is kind of going to go by the wayside. It doesn't give you kind of fancy clustering abilities, but this is a basic bit of replication and some fault tolerance. So pictorially, again, we should be able to see two instances of the same service. We're treating this bottom one, matching engine 1, as our source of truth. Data's going into that ring buffer, and before we journal it or process it, we're sending it to a cloned instance. So we know that all the events that other instance is going to get are the same events in the exact same order. And once they've gone to that other instance and it's acknowledged receipt of it, we can then, on both of them, concurrently process those events. We can journal them on both services. Our application thread can process those events on both services. Ideally, on the non-live replica, you don't want to output the events to the rest of the world, otherwise downstream consumers are going to get double the traffic. But this is kind of a rough way of doing replication and replicating that state machine.
And interestingly, both of these replicas will do exactly the same work, produce exactly the same outputs every single time.
They should.
They will.
We'll find out if they do in a minute, because one of the steps to testing that is snapshotting as well. So we talked about replaying these journals. Those journals begin at the beginning of time. If you need to get to the state a day later, a week later, a year later, you need to replay all those journals. That's very expensive and will take quite a while. So instead, you can pause your entire system and record that in-memory state. We've consolidated our state to one service now. Let's record it. This means that you can pick up that state, that snapshot, and replay journals from that point and get to any other point in time, which gives you much quicker recovery. And journals will fill the gap between the initial state and where we're up to. When you're doing this, recording that state, you need to stop all inputs and outputs. You probably don't want to be doing this on your live running system, but that's one of the joys of having a replicated system. We can take those snapshots on a replica system. So an example, if we had a system like this, we might want to record any kind of state objects in that application thread. We also might want to record the contents of those ring buffers as well, because if we're going to restart our service and have it pick up from where it left off, we need all of its state.
And the snapshot will know which sequence to start from. What is the next sequence that you haven't processed?
Yeah.
And it will always do it exactly the same time.
It's one of the benefits of sequence numbers on your buffers. But a lot of this relies on us actually being deterministic. I mean, we've said we hope it is, and that you replay these journals, it'll generate the same output. How do you know if it does? Well, one of the ways is you can have two snapshots that should be of the same time point and compare. So if you imagine a live running replica service, it can take a snapshot at T0, some journals happen as time moves on, and then we take another snapshot. We can take that original snapshot, replay the same journals, and generate a new snapshot, and these should be binary equivalent if everything's gone well. And if they haven't, you don't have a deterministic system.
And what can go wrong, Nick?
Well, there's a few common pitfalls if you're writing an application that you expect to be deterministic. We listed a few here. So using the wall clock time, if you want to attach a time to any of the events as you're processing, picking that from system current time millis, probably a bad idea. One of the things we do is, we attach timestamps to events as they go into that first ring buffer, and that is our source of truth time. Nowhere should we be asking the system what time it is.
And the actual result of that is that once you take the snapshots and the journal and replay it locally, all the timestamp that you see will be visible exactly as if it would happen in production at that time.
Yeah.
A day ago, a week ago, a minute ago.
A decade ago in some cases. Other common pitfalls, unordered collections. If you are snapshotting your state and it's a hash map, you're going to have to iterate through that hash map to record it. And then in your recording, when you reload your snapshot, you're going to have to iterate through it again and put it back into a hash map. That collection doesn't have guaranteed order, so you might get the same data, just not quite in the same order. And a real clanger for any deterministic system is producing side effects, which we kind of touched on earlier. What side effects are there? Database calls, RPC, having a HTTP endpoint that people hit, or JMX endpoints that people try and poke different state in. Bad things.
What do we really have to block here?
Yeah, it's a common thing that a lot of people say, I need to talk to a database. I've in a financial service, I've created a trade, I should record that somewhere. And you're telling me I can't put it in the database? Well, not quite. Your entire system should probably have multiple services in it. Not all of them need to be deterministic. So you can have a downstream service which just archives things in a database for you. That doesn't need to be deterministic. The output from that matching engine, which said a trade happened, that is deterministic.
And so, that's the source of truth.
Yeah, and that gives you determinism and some blocking in there. So hopefully this covers a lot of the benefits that we previously described. You get predictable behavior. Hopefully, it's the whole point of being deterministic. You get debuggability. You can take those journal files from any production system and replay them locally on another machine, be able to check a production issue or a query of why did this happen. You get some level of resilience via replica services, and you get a lot of simplicity because we've kind of cut our problem space down to a single thread and quite a small service. So I think that covers everything that we were going to talk about.
Oh, really? What about performance? We mentioned the application thread before, and if you would like to make your system deterministic, You should only update the state with one writer. That will give you a deterministic behavior, but what it also can give you is extreme performance. It might be very important for you. It is very important for us. How fast can it go? Well, it depends. What do you have in your business logic? So only update state from one thread. You might ask yourself, why? What? Single thread? But everyone told me to like parallelize.
It goes faster, right?
Sometimes it gets faster. Oh, does it? Well, concurrency is hard. If you look at this code, can you tell me whether this piece of code is thread safe? Hands up.
No one. No one thinks that's thread safe.
So the point of this particular code is to safely increment a variable, right? You could do it with atomic long, atomic integer, just get an increment or increment and get. However, what if you want to bump up your state by 10? Do you want to execute increment and get 10 times by multiple threads? Fortunately, JC Stress can prove to you that, for instance, using 3 threads, this thing is absolutely thread safe. However, it is not deterministic. I created a set of benchmarks where, not unsurprisingly, the plain writes to a Java variable are insanely quick, assuming that you execute them on one thread. But also similar to compare and set, monitor, synchronized. Every single time when you have any lock in your code, if you execute this code on a single thread, this should be the fastest possible execution. Whenever you try to use more threads, you're going to get contention. And these updates, if you don't want to miss any of those increments or any other updates, we'll have to wait. We'll have to wait until the actual conditions for this update are correct, so that your update is not missed. Obviously, I didn't test volatile and plain with 2 threads. Obviously, not thread safe. So there is no point of testing anything more in this scope. So when you're using a single thread for your updates, treat it well, because you only have one. What does it actually mean? Imagine that in a given time frame, you would like to execute a bunch of updates. And you have your single thread. You have your single writer that can update the state. If you mix it up with I/O, you're wasting time. You're polluting the one most important and one most precious resource in your system to do stuff that you can do somewhere else, maybe downstream. You have journals. You can execute your updates on your in-memory state. Do you have to persist it on this thread now? Really? Can't you do it in a downstream system? If anything fails, you can always recover, replay it, achieve the same state. If you clean up your thread and make it do only the absolutely necessary work, suddenly you have a lot of space to do a lot of updates. You can handle bursts, bigger bursts, until your thread will eventually get fully utilized. At this point, you might be reaching a capacity of your thread. So whatever tries to execute an update, whenever you try to consume, you will not be able to consume from the ring buffer fast enough, ring buffer will fill up. Everything that tries to publish to a ring buffer will suddenly not be able to. So this might provide you with a natural back pressure where the whole system slows down to actually try to execute every single update safely, quickly, as quick as it can. And it is totally possible if you make your thread do only the necessary work. So what is the outcome of this kind of this architecture? Suddenly it turns out that a lot of the simplicity comes from lack of any locks on your shared states. Whenever you're trying to figure out what happens in runtime in production, you know that it was only one writer that could change it at this point in time. Any weirdness that happened in production happened in the previous execution of this thread. You're going to get the fastest execution possible, and eventually reduce jitter once you isolate your CPUs and pin this thread to this isolated CPU. There are some tools to help you out. LSTOPA will show you the layout of your machine, how the cores and caches are organized. You can use CSET task set to pin the whole process, or you can use TUND to create a profile where you say, I want core 1 and 3 to be isolated. The rest of the cores can do regular jittery work.
Yeah, I think it's important when you've got one thread to pin your thread, especially when performance is key. Going back a few slides where we had kind of time interspersed with I/O, if the kernel schedules another process on your core, well, suddenly you're not executing. You're kind of off that CPU. So making sure cores are isolated and that you ping your thread to that core means that you will hopefully get a lot more utilization out of it and not spend time being beaten by another process.
Ah, these schedulers. You're also going to get a very predictable execution time, which is quite important when your clients expect you to be responding to them in around 80 microseconds. So why are the single thread updates better? They are very easy to read. The code is very easy to read and reason about. CPU is very happy. And eventually, these updates can be made deterministic with ease.
With ease.
Thank you for coming.
Yeah.
That's all we have for you today. You can find the sources that we mentioned earlier.
We've got a cheeky link to the LMAX careers page on there, just in case any of you want to work in financial systems in London. Just an option out there. We are recruiting in New York, so if anyone's from New York, probably well worth looking at that page. And
are there any questions?
Questions, I think we can tap. No questions. People can probably just shout out questions if they got any as well. Okay, what if the system is modified, is not backward compatible, and the previous events cannot be replayed? Is there a solution to replay these events? That is a really good question, actually. So with your event space and the way you kind of serialize events, the way you journal them, you always need backwards compatibility for this to work. So you can do that in several ways. You might version your events. You might use a kind of protocol. So protobuf makes it quite easy to extend events if you need to change them. And it usually comes with a contract that you can't kind of remove fields. You either null them out. In the one we use internally, it's very kind of versioned. Yeah. So most events have an identifier of this event is of this type, that will always be there. If you need to change it, you create a new kind of event type, effectively. Those are a few ways to solve it. I'm sure there are many others.
And it's also easily testable, right? Once you provide a new version of serializer that can deal with new version of this event, you can easily verify that whatever you're producing, journaling, can be easily read, regardless at which point in time you actually journaled it.
Yeah, and I think as well, one of the other things is when you have new versions, we tend to remove the ability to serialize old versions, and we just keep the deserializer around. That way, you don't accidentally use the version of the order serializer from 3 years ago. Can help you there.
Yeah. There are many ways to ensure that you're serializing and deserializing correctly.
Yeah. Okay.
What to do when one thread is not enough? Great question. Sharing, partitioning.
Sharding, I think.
At some point, yes. At some point, you might get into a situation where you are at capacity of your CPU, and single CPU time is not enough to execute the whole work, to process the whole workload. In this case, you need to shard your state and redirect it to the correct machine.
Yeah, I mean
that is responsible for this bit of your data.
Yeah, an example might be of a trading system. If you've got different things you can trade, so we work in FX mostly, so euros to dollars, euros to GBP. Those are could be run on separate matching engines because those are separate order books. People don't trade between them, they trade on one. So that's quite easy for us to partition. I say there's a few caveats to it. It's not that easy.
It all depends.
But it can be done.
It all depends on your business domain, right? If you can find a good discriminator with fairly low cardinality, I would say for a start.
Yeah.
That might be a good start. Then you might start to chop it further.
Yeah. There's one there. What are some practical examples? Would be very helpful, as it sounds pretty complicated. It's not that complicated. It tends to simplify a system. In terms of things like frameworks, so for, say, buffering, there's always the disruptor, version 4 coming soon. There are other frameworks out there for inter-process messaging. So Aaron is a big one in this world that deals with a lot of that ordering. It does journaling for you. It does state snapshotting stuff, I believe. And I believe they've even got deterministic testing now, although I haven't used it myself. So there are frameworks out there. In terms of existing systems, I've only really worked at LMAX that does things this way. Previously, I worked in government, and they didn't do this. So it's kind of niche, I'd say.
I think that a good example would be account balances, or for instance, gambling, or anything where client money is involved.
Another one might be gaming. So I know a few game servers. I think Riot, the people who make League of Legends, awful as it is, they have quite a good tech blog, and they talk about being deterministic. If you've got multiple people gaming on the same server, if I move forwards, hopefully Raf sees me move forwards as well. If he tries to shoot me, that either shoots me or it doesn't. It shouldn't be different between those things. So there are use cases outside of financial worlds, and maybe there are more use cases we're not aware of. Yeah.
Ping us after the talk. We can try to figure out how to do it with your domain. What happens to persistence if they're not done in the writer threads? Can we guarantee that threads will read the correct states? So usually in systems like this, you want to persist after you're actually change your state. You would like to produce an output, get a response back to the client. If you have all your persistence downstream, assuming that a service receiving that and all the database schemas allow provide item potency, it shouldn't be a problem, right? If you imagine a system with hundreds of tables, and you're gonna get one table locked, broken. You have a gap in your data, but it's downstream. It might be used to provide some statements, some history, some visibility for your client, what just happened. There is a partial outage, but you can take the journal, you can replay all the events that happened within this time frame, reproduce this state, send the output to the service that just failed, insert those missing records into the database, and just execute an update on a production system, because you're absolutely sure that the timestamps are exactly the same. All the states that led to the record that you're missing, to the data that you're missing, is exactly the same as if it wouldn't fail. Does that answer your question? I hope so. Can we guarantee?
There's probably some other bits there of when we message, say, a downstream service, if we make sure that's done over, say, a reliable messaging system, so that it will know if it misses any messages and re-request them automatically, hopefully while they're still in cache. And yeah, in a disaster scenario, we can just replay journals and get those events again.
Yeah. So ring buffers provide you with some sort of time buffer, right?
Yeah, and
in an event
because it's a ring, it will wrap. Yeah. So it won't store history forever. The journals will have that. Yeah. But in a running system, if a downstream service gives some kind of negative acknowledgement, hey, I seem to have missed a packet, that might still be in that buffer upstream. And so we might be able to resend it. Not always, but hopefully most of the time, if it happens. How does replication affect performance? It's a good question as well. In the diagram, I said it replicates first, waits for an acknowledgement, and then it processes. That does have an effect on performance. We have some kind of safeguards in there so that if our replica services were not responding, we're not going to wait forever for an acknowledgement. We will move on and we will run at risk with no failover, no clones or backups. But that is something that we would take to keep that performance up. And the way we talk to that other service, which is replicated, so it's likely on another machine in the same data center and potentially in another data center entirely. So the way we message needs to be quick. We're not doing REST APIs for that. And if it's in another kind of geolocation, we might not wait at all. We'll just hope, because it's very rare you fail over to DR, so it's usually all right.
What event bus do you use, or do you rely on tons of disruptors? We rely on tons of disruptors.
Yeah, there's quite a few, but disruptor is only inter-thread communication, so it won't do inter-process or over the network. For that, we use there's kind of a proprietary framework internally for doing most of our messaging. And when it gets down to the network layer, at the moment we're using a thing called Ultra Messaging System Service, UMS. It's from Informatica. But kind of mentioned earlier, there's a thing called Aeron, which does a lot of this and does it really, really well. And I think Chronicle, that they also have quite a few frameworks for doing this kind of thing.
Have in mind that having tons of disruptors, well, might be a bad thing. However, if you have just a handful of disruptor, you need to have in mind that disruptor is not like this big, giant machine. It's a tiny class with tiny array doing one thing very, very efficiently. So you can have lots of them. It's not a holy cow, right?
Yeah, it's an array with some pointers into it. At its most kind of trivial boiled down.
Yeah.
With some nice DSL around it.
So if you're worried about having 20 disruptor in your single service, it's totally fine.
Yeah, I mean, one of the things to consider with something like the disruptor is it pre-allocates the full array first. Yeah. For efficiency and speed, you want to be cache efficient by having all your objects in a line next to each other and so on. So if you have lots of disruptors and you make them nice and big so you can do your replays, you might find yourself running out of memory. And you might need to think about how to efficiently size those buffers for the use cases, whether they be disruptors or other buffers. And there's another question there. Do you like Krakow? I found it pretty good so far. I've never been here before. Raf took me and some of my colleagues to a jazz bar. One of my colleagues really enjoys jazz, had a great time.
I absolutely love Krakow. I used to live here for a few months, almost a year, like a decade ago. So
Yep.
I know my ways around here. I have my favorite pubs. I absolutely love it.
I'm around for the weekend and open to ideas of things to do. So if there's any locals who want to tell me to go visit some stuff, let me know. And I think that's all the questions. So again, thank you for coming. Thank you for listening.